All right, so I told you I was gonna make a second video as it pertains to motion along a line, okay? Now that could be like the x-axis, that's the horizontal axis, that could be the y-axis, the vertical axis, or some other line. But when I talk about motion along a line, you're either moving up and down or left and right, okay? So I just want to relate this, to some things that we've talked about so that you can apply it better when you do some practice problems. So just real quick, instantaneous velocity. Remember that's that's the velocity at a specific point. You get that by taking the derivative of the position, and remember it gives you a rate, right? And it's a rate at which the position changes. Okay, it's a rate at which the position changes. So think about all those problems where we had to describe, we had to explain what the derivative meant. Okay, and so if it was like the rate of change, if our answer was like degrees per second or something, it was the rate of change of the temperature over time, so just think about that. All right, so velocity, we talked about this a little bit in class today. It could be measured in feet per second, maybe meters per second. Another common one is miles per hour, okay? Those would all be considered velocities. And here's what I want you to remember and relate back to your connections between derivatives and stuff, okay? The sign of velocity determines the direction of movement, okay? Just like the sign of the derivative, like when we're talking about graphs like f and f prime, the sign of the derivative tells you if the original is increasing or decreasing. So when we relate that to velocity, the sign of velocity determines the direction of movement. It tells me if my position is changing in terms of, is it moving to the right and left or up and down and that sort of thing. So the sign of velocity determines the direction of movement. Okay, so if velocity, right, is positive, we say that by saying it's greater than 0, then we know that the object is moving in a positive direction. Okay, well, that would mean up or right, depending on what kind of motion it is. If the particle's moving up and down, then positive means up. If the particle's moving right and left, then positive means right. If we're just talking about a standard function, the derivative being positive means the function is increasing. Okay. Alternatively, if the velocity is negative, then the object is moving in a negative direction, which would mean down or left, depending on the type of problem that we're looking at. Okay. And then keep in mind that if velocity is equal to 0, the object is at rest, or sometimes we say that that's the same thing as when it's changing direction, but it only changes direction if the sign changes. Okay, so if velocity equals 0 and there's no sign change, then the object is just at rest. But if the velocity equals 0 and there is a sign change, meaning it changes from positive to negative or negative to positive, then we definitely know that there's a change in direction. All right, it's taking a brief rest and changing direction. Okay, and then we're going to go ahead and extend that to acceleration. So acceleration is also a rate, all right, but it is the rate at which the velocity changes. Okay, it's the rate at which velocity changes. So remember, acceleration is the derivative of velocity. Okay, so that also means that it is the second derivative of position. And the units that it typically gets measured in, feet per second squared. meters per second squared. If we did miles per hour, it would have to be miles per hour squared, et cetera, okay? Now, the sign of acceleration, which remember is the second derivative, so think it back to our connections, the sign, okay, of the second derivative or acceleration will determine if the first derivative is increasing or decreasing. So in this case, that means that will determine if velocity is increasing or decreasing. All right, so you can go back and see, and that does agree with the connections that we made previously on the second derivative. Okay, so how does it work? Well, if acceleration is positive, then velocity is increasing. If acceleration is negative, then velocity is decreasing. And of course, last but not least, if acceleration is 0, that means velocity is not increasing or decreasing. But that doesn't mean it doesn't have velocity. It just means that the velocity is staying constant. Okay, it's not increasing or decreasing. Okay? And then just to reiterate some other things that we've talked about, okay, speed, all right, is the absolute value of velocity, okay, and it only measures forward progress. It doesn't matter what direction it's going in, okay? Now, if I want the speed at a specific time, okay, which we saw earlier, you just take the absolute value of the velocity at that time, okay? But if I want to know if an object is speeding up or slowing down, that depends on the sign of both velocity and acceleration. If they have the same signs, the object is speeding up, right? So speed is increasing. And if they have different signs, the object is slowing down. That's the same thing as saying the speed is decreasing. Okay? All right, so now let's put some of that to work and look at some problems on particle motion. Okay? So our first example here, it says a particle is, oh, I'm missing an I, moving along a horizontal line, so that means it's moving back and that means it's moving back and forth. Okay, it doesn't have to stay only going to the right or only going to the left. It could change direction. And this time I'm giving you the function. Okay, so it's not based on free fall. And I just want to know what is its position at the beginning, and which means the position at time 0, and then the position after 1 second, and the position after 2 seconds. And this would be a good time for you to pause the video and work these things out. Okay? Now, I don't put units on it because I wasn't given any units. All right, next question. When is the particle moving left, right, or changing direction? Okay, well, if you were taking notes a minute ago, okay, we said that the sign of velocity determines direction. Okay, the sign of velocity determines direction. So that means I need velocity. Okay, so I'm going to take the derivative. A couple power rules here. Okay, so there's my derivative. And then I need to figure out how to get its signs. All right, and to figure out signs on a function, I mean, technically you could graph it, but you should also be able to do it without a graph. Okay, and so what you want to do is you want to set your velocity equal to 0 and factor it. So I'm going to go ahead and take out the GCF to save myself one step of writing. And I'm setting it equal to 0. Okay. And then I'm going to factor the rest of the way. And I get, let's see, did I do something wrong? What multiplies to be 12? Oh, yeah, because they're both negative. So -6, -2. Okay, so t equals 2 and 6. Now, all that means right now is that you know the particle is at rest at time 2 and 6. You don't know if it's changing direction unless the sign changes, okay? So how do I do that? Well, we're going to go back old school and we're going to make a sign chart, okay? And that means you need to list the factors that you got when you factored your polynomial. And then you need to find the zeros. What would make each of those factors 0? Well, the 3 will never actually equal 0, and it's positive, so technically you don't need it, but I'm going to show you that, you know, like just as a rule of thumb, you know, keep your constant. All right, and so let's see, I need a positive 6 for the second factor and a positive 2. And so I want to put those in numerical order from left to right. And then I'm going to draw my choo-choos. I think Miss Damon just draws lines. I call them choo-choos, okay? And then we're going to fill in the signs, okay? Well, 3, we just said, is always positive. So literally you put all pluses, which is why you don't need it, because positives don't make something change sign. It's only negatives. All right, but then if I plug in something bigger than 6 into t minus 6, I'm going to get positive numbers. But if I plug in something smaller than 6, I'm going to get negative numbers. And the same thing for 2. If I plug in something bigger than 2 into t minus 2, I get positives. And if I plug in something smaller, I get negatives. And then remember, these were technically all connected by multiplication. So you need to multiply all the signs together. Okay? And because the signs change, okay, you know, it's positive before 2 and negative after, and then negative before 6 and positive after. The signs change, okay? Both of these are when velocity changes direction, okay? Now, the other thing that you can get from this sign chart is when is it moving right or left, because a positive means right and a negative means left. But you do need to convert those to intervals, okay? So when is the particle moving right? Okay, well, typically we would say negative infinity to 2, okay? But we're talking about time, and time can't be negative. So we actually start at 0, and we move right until we get to 2. And we don't actually include 2 because that's when we're changing direction. Then we move left from 2 to 6, and these are seconds. And again, we don't include 6. We don't make a bracket because that's when it's changing direction. And then we move right again from 6 to infinity. Okay? All right. Now, if I wanted to represent the motion on a number line, okay, I need a couple of things. I need to, like, I'm representing the motion, so I'm using actual positions, okay? But I need to know what is the position when I start, okay? And then what is the position anytime I change direction, okay? And so I change direction at 2 and 6, so I'm going to need all of these positions. Now, we already found S of 0 in part 1 and S of 2, but we would have to go back and plug in 6 into that original S of t function, okay? And then I'm going to draw a number line. Try to keep it as straight as possible. I ran out of space here on my tablet. Okay, and so somehow I have to show that I can go all the way from negative 24 to 8, okay? Now I'm going to count by 4s, just because I know that it'll fit nicely. Oh, I don't even need all this extra space over here, which is fine. Okay, I don't need any of this. All right, so what you want to do when you're graphing, representing the motion, okay, you need your starting point, all right, and we don't want to graph it like really on, like, in, you'll see what I'm talking about. Okay, so now we have to base it off of when we're moving right and left, okay? So we start at negative 24 and we move to the right for 2 seconds. This is seconds, okay? And but over here, this is where we go. All right, so we go from negative 24 to positive 8 in 2 seconds, and we're moving to the right. Well, we better be moving to the right. That's the only way to get from negatives to positives if we're going left and right. Okay, now instead of going left, backwards, right on top of that, I'm going to show that I actually turn and go back to the left. Now I go left from 2 seconds to 6 seconds, but that takes me back to position negative 24. Okay, so I'm going left until I happen to get back to my starting position. Sorry, I'm having trouble with my arrows staying straight. Okay, so I'm going left, and then according to this, I turn and go right at time 6. So I need to show that I'm changing direction, and I'm going to the right forever. Okay, that's what we just said in the previous question, that we keep going to the right forever. Okay, now technically this motion is back and forth on the same line, but the way to show it is to kind of use those arrows and go up a little bit. Okay, all right, moving on. When is the velocity increasing or decreasing? Well, if you'll remember, we just said on the previous slide that velocity, or excuse me, the sign of acceleration determines when velocity is increasing or decreasing, the sign of acceleration. So that means I need acceleration. And that is not a function I have found yet. I need to go back up, find my velocity, and take the derivative of it. Okay? And then I want to know the signs. Okay? Well, to make a sign chart, I'm going to want to factor this thing so that I know when velocity changes from increasing to decreasing or vice versa. And then on my sign chart, I'm going to leave the 6 off this time because it is positive. But if it were negative, I would definitely need a line for it. You know what? I'm going to put it just because it's a good habit to get into. Okay? So I'm going to put a 6, but it doesn't have a 0, so keep that in mind. My only 0 is 4. So when I draw my choo-choos, 6 is always positive, and t minus 4 is positive when numbers are bigger than 4 and negative when they're less. So then I'm going to combine my signs. And here, the negative means velocity is decreasing, and the positive means velocity is increasing. Okay, so velocity decreasing, and I need an interval. And remember, we're dealing with time, so we want to start at 0. And then velocity is increasing from 4 to infinity. Okay, so that means velocity, right, is not increasing or decreasing. It's changing from increasing to decreasing at time 4. It's staying constant at that very instant. All right, and now it's a very different question when I ask if when speed is increasing or decreasing. So I don't want to know is it increasing or decreasing. I want to know when is it increasing or decreasing. And these are intervals. Okay, now if you had a graph, you could graph velocity and acceleration in the same window and look at when they're both above the x-axis at the same time or both below the x-axis. But I want to do it with signs. So remember, when they have the same sign, speed is increasing, and when they have different signs, speed is decreasing. So if you actually make a sign chart that puts everything together, that you put your v of t and your a of t together, you look at your 2 sign charts and you combine them, okay, then you can figure out speed increasing or decreasing. So if you go back up, hopefully you can see it on your paper, velocity was equal to 0 at 2 and 6, and acceleration was equal to 0 at 4. So I'm putting those numbers on this line in numerical order. And then I'm going up and I'm taking the answers from my velocity chart. And it said that velocity was positive before 2, negative between 2 and 6, and positive after. And then I'm going to do the same thing for my acceleration chart. The acceleration sign chart said negative before 4 and positive after. And now all I have to do is look to see when the signs are the same. Okay, and that's when speed, whoa, sorry, having trouble here. That's when speed is increasing. And then I can look to see when the signs are different, and that's when speed is decreasing. And so then I would want to get intervals for that. So it looks like I'm decreasing first. Speed decreasing. Remember, we're starting at time 0. We're going to 2. Then did it again. Speed is increasing from 2 to 4. Then decreasing again from 4 to 6. And then increasing again from 6 to infinity. Okay? All right, and the last thing I want to look at is how do you determine total distance traveled? Okay, how do you determine total distance traveled? Well, it comes from position, okay, but you do have to take into account if the particle changes direction, okay? So it's going to be, you're going to have to find intervals of like when it's moving right or left, and you're going to have to break those intervals if there's a change in direction. But you're going to use the formula distance equals the absolute value of the position at the end minus the position at the beginning, okay? Because total distance traveled is a positive value. So I'm still working with the same problem, and I want to know the total distance traveled from time 0 to time 2. Well, the first thing you have to ask yourself is, was there a change in direction in that interval? And if you go back and look, we did not change direction until we got to time 2. So there was not a change before that. So for this one, we can just do the absolute value of S of 2 minus S of 0. Okay? And so again, those are just values that you need to work out. S of 2 was 8. S of 0 was negative 24. You do the math first, and then if it were negative, you would take the absolute value of it. But 8 plus 24 is not negative, so I'm done. Total distance traveled is 32 units. I don't know what it is, feet, meters, whatever, but they didn't use units in this problem. All right, but if I ask you for total distance from say 1 to 3, but we know that the particle changes direction at time 2, we're going to have to break the interval. We're going to have to actually find the total distance for the interval from 1 to 2 and then add it to the distance for the interval from 2 to 3. Okay, and so my total distance, all right, is going to come from these two absolute values. Now, some of them we may have worked out, some of them we may not have, but you will want to go back and work them out. And I do encourage you to do that and make sure that you get total distance is 12. Okay, and so I hope that answers some questions that you might be having. And I'm sure that we'll see problems like this again, but I just wanted to put it out there. I really do encourage you to watch these videos. Obviously, if you're still watching, then you did what I asked. But okay, hope that helps. See you in class.